All right, remember we were discussing the abelian Higgs model, and we transitioned from the Coulomb phase at positive mass, studying the Higgs phase at negative mass. Let me remind you what the Lagrangian looks like. There's the Maxwell term, there's the kinetic term for the Higgs. And now we're in the Higgs phase, so there's a potential here, which looks something like minus m Higgs, or sorry, I'm using conventions in which m Higgs squared is negative. So m Higgs squared plus h to the fourth, something like that. All right, so we're in the Higgs phase, h gets a VEV. That's what we started discussing before lunch. And I think we had a brief discussion about the fact, remember that this model has two one-form symmetries. It has an electric one-form symmetry, which is ZQE, where QE is the electric charge of this guy. There's a ZQE electric one-form symmetry, and there's an unharmed U1 magnetic, because there are no magnetic charges in this, no dynamical magnetic charges in this model. And I had made a brief comment about the fact that in the Higgs phase, right, the gauge group is completely, the U1 gauge group is Higgs down to ZQ, and the fact that this ZQ gauge theory realizes this this ZQ one-form symmetry in the spontaneously broken phase. So this is spontaneously broken. And that's related to the fact that you have a gapped phase, but with a ZQ gauge theory in the infrared.
What are the physical consequences of this ZQ gauge theory in the infrared?
Well, I mean, there are non-trivial line defects and non-trivial surface defects. Maybe I'll discuss them in a little bit. There is non-trivial degeneracy on manifolds other than the sphere, for example, tori.
But suppose you're a particle physicist, you want to scatter things, you know.
If you're a particle physicist, you're blissfully ignorant of all this richness.
Nothing for which shit.
No.
Nothing for superconductors.
Sorry?
Nothing for superconductors.
What do you mean?
Like the Z2, when you break the VCS.
No, but I mean, I think if you're a person whose point of view is that the only observable you care about is the conventional S matrix, then this Z2 gauge theory doesn't do very much for you, other than the fact that you might have particles, massive particles, in the theory that carry Z2 gauge charge. And you can scatter them. But if you just scatter particles in 4 dimensions that carry Z2 gauge charge, okay, in principle they carry some Z2 Wilson line to make them gauge invariant. But because Wilson lines can't really braid in an interesting way in 4 dimensions, you know, these Z2 Wilson lines don't add much to the S matrix. If you scattered particles in strings or something like that, you could maybe get some Aharonov bomb phases that would be more interesting.
Actually, is this Z2 Wilson line, can it wrap up and make a massive excitation? Can you make a massive excitation on
No, because this is a deconfined Z2 gauge field, so I don't know how to do that. Yeah, I mean, this is, at long distances, this is just a TQFT, right? I'm saying if you have massive particles, I mean, you do have massive particles in this model. For example, you have the Higgs, and of course the Higgs itself will not end up carrying any ZQ Wilson line. In order to have something that carries the ZQ gauge symmetry, you need to add additional matter, like for example some fermions with charge 1. Then you would break the one-form symmetry completely, but you would actually have some matter that you could scatter that was charged under the Z2 symmetry. Right. I would say the invariant kind of robust content of the low energy TQFT is in the fact that, you know, it realizes these symmetries in a particular way. So saying that there's a ZQ gauge theory at low energies and saying that there's a ZQ one-form symmetry that's spontaneously broken is almost the same thing. All right.
So just to clarify, it's not gapless because it's discrete.
Sorry?
It's not gapless because it's discrete.
Well, the photon gets eaten, right? The usual Higgs mechanism.
Well, it's not a gauge, it's a global symmetry. I mean the GQE one-form symmetry
Yes.
that is continuously broken, but there's no Goldstone boson, just that one.
That's right. There's no Goldstone boson because it's discrete. Yeah. So this one can be spontaneously broken, and it does not result in a Goldstone boson. This one, if it were spontaneously broken, would result in a Goldstone boson. But we know that there are no massless particles. So this one is in fact unbroken.
But suppose if I am in a very high energy, so that like I restore the one function.
No. Symmetry breaking is a low energy question. There's no such thing as symmetry breaking at high energy.
And in this case, there are QE by QR on even in flat space, or just an interesting manifolds?
I think we had a variant of this discussion before. No, so there.
Also here, there are no.
Yeah, it's the same story always. You know, you have multiple vacua on interesting manifolds. You do not have any. You have a unique vacuum on the sphere. So that's it.
So then for the sphere, can you say this is trivially gapped?
No, trivially gapped. I mean, to the extent that the word trivially gapped is well defined, the sense in which people use it is that there is really nothing. There's no topological order. There's no TQFT. Yeah.
Is it possible to obtain the effective theory, so like the Chern-Simons theory, which kind of?
Yes. Yes, you can do that. And in fact, it's something that, given enough time, I could show you how to do. But it's also a nice exercise. So maybe I'll give it as an exercise. So the exercise is the following. The low energy effective theory of this model can be derived in the following way, and it combines with something that you did on the homework yesterday. So deep in the Higgs phase, right, the radial mode of the Higgs field is very heavy and is frozen. So you can essentially approximate the Higgs field by its VEV, which is some number, times its phase. The phase is, classically a massless Goldstone boson that then gets eaten by the gauge field to give you the Higgsing. So yesterday on the homework, I asked you to work out abelian duality in different dimensions and for different form degrees. So in 4 dimensions, you can dualize the compact chi field. Chi is a compact scalar. And in 4 dimensions, a compact scalar is electric magnetic dual to a 2-form gauge field. And then dynamical 2-form gauge field, little b. Okay? Where, dB is star d chi. And when you do this duality and you plug back in to the abelian Higgs Lagrangian and you only keep the light modes, you throw out the mass of Higgs, you throw out the mass of photon, then at low energies in the d pi r, this theory flows to a BF theory. So this is exactly what you're asking for. This is a it's not a Chern-Simons theory, it's a BF theory, but it's a little bit like a Chern-Simons theory. It's an abelian theory of forms, and it's a TQFT. So this is a TQFT that represents, among other things, unbroken ZQE gauge symmetry. Right. This B, when you do the path integral over this B is a 2-form gauge field, so it has fluxes which are quantized and so forth. When you do the path integral over BE, you restrict F to be flat, and you restrict its holonomies to be valued in ZQ. So that reproduces for you the ZQ unbroken gauge symmetry. And this TQFT has interesting line operators. It has the Wilson line of the A gauge field, right, which are topological at long distances. It also has these surface operators, and they link non-trivially with each other. The other thing that you can use this, after you derive this description, the other thing that you can use it for is you can now restore in the original Lagrangian the B electric and B magnetic background fields. And when you do that, you will find that B electric accompanies F in this minimal way that we discussed previously. And the coupling to B magnetic is unmodified. B magnetic still couples to F in this way. And you can check that this coupling of the BF theory to background fields correctly reproduces the anomaly, the mixed anomaly of B electric and B magnetic that we discussed previously. So this unbroken ZQ gauge theory, or this TQFT, is essential for correctly matching the anomalies. The only exception to this is when QE is 1. And then the anomaly trivializes. And indeed, then we would say the theory is trivially gapped. All right.
So should here F be 0 on shell?
No.
Sorry, never mind.
Why?
No, I didn't say the BE. Yeah.
Oh, sorry. Without the BE, F is 0 on shell.
Right.
Yeah. So that's the statement. F is dA. Remember? F is so F being 0 on shell means that you don't have fluxes. You just have flat connections.
Yeah.
And then on top of that, the fluxes of B tell you that the holonomies of this flat gauge field have to be in ZQE.
The magnetic symmetry is not broken to ZQM?
Nope, it's not broken to anything because of what we said before. If the continuous symmetry were broken, you would have a massless Goldstone boson. In fact, the U1 magnetic is completely unbroken. So let me go and explain that.
Now in the IR, when I have my BF, now F2 isn't also constrained to be by the equation of motion, the gauge field isn't constrained to be also a QE gauge field?
Yeah, I just said that.
So then the coupling, the one BM wedge 2, it's a bit confusing to me.
I leave that for the exercises, and I'm going to move on. I was instructed to ruthlessly move on. Yeah. Anyway, this discussion can't really be had until you actually work through the exercise. So I'll be around later, so we can discuss it then. All right. Let me explain why this is true. I mean, so we know that it can't be broken because otherwise there would be a Goldstone boson. But that should mean something for the 't Hooft lines, right? Remember, which are the things that are charged under the symmetry, and for what they do in the theory, and that's a beautiful story. So remember, the 't Hooft lines, right, were the magnetic dual of the Wilson lines. They were world lines of magnetic probe particles, and of course, in the spontaneously broken phase, they had, perimeter law, and they had a VEV. And somehow the statement that the U1 magnetic is unbroken must mean that now they do not have VEVs. It must now mean that the VEV of every large Wilson loop actually goes to 0 as you scale up the loop. So let's see how that actually happens. Well, the way it happens is related to the concept of area law that was mentioned earlier in the morning. So because the theory is gapped, when you act with the 't Hooft lines on the vacuum, right? The 't Hooft lines try to create magnetic flux. They're essentially thin collimations of magnetic flux. In the Coulomb phase, that flux can spread out. But in the Higgs phase, because of the Meissner effect, the flux is confined into thin tubes. And what that means in practice is that if you take your vacuum at some fixed time slice, t, and you act with an 't Hooft line at this fixed time slice, then you create some kind of object that carries magnetic flux. And in this abelian Higgs model, this is famously the kind of collection of ANO magnetic vortices, Abrikosov-Nielsen-Olsen magnetic vortices or superconducting vortices, or so strings. Objects, dynamical objects that are one-dimensional in space and one-dimensional in time, and the 't Hooft line in this unbroken U1 magnetic phase is the creation operator for these magnetic strings. And the magnetic strings are protected by the unbroken U1 magnetic. So they, for example, if you take Qm to be 1, if you create a fundamental magnetic string, it cannot decay. It's completely stable. If you have a string of charge 2, in principle, it could separate into 2 strings of charge 1, or it could form a bound state. That's a dynamical question. But the total string charge has to be conserved. Now, try to remember the picture that we had that related the static potential to the behavior of large loops, right? We drew a large loop, large rectangular loop in the kind of RT plane, right? Looks like this. Now I'm taking this to be in a 't Hooft loop of magnetic charge Qm. This is this rectangular loop. And now I'm saying that this bottom segment of the loop creates an ANO vortex, an ANO string of length r, right? Now, because the ANO string has finite tension, you can check that. You can find soliton solutions for them and compute their tension. Right? So that means that the energy of a long stretched string will be, roughly speaking, this tension times the length of the string. Now, this product, the tension times the length of the string, is the area of this. Oh, I'm sorry. I screwed it up. Different T. I should call it sigma. I shouldn't call it T. I'm confusing myself. Right. String tension times R. OK, great. Now let's plug this into our formula for the large loop. Remember that the large loop the expectation value of the large rectangular loop scales like e to the minus t, where t is the time axis of the loop, times the scalar potential. As a function of r, here I'm neglecting the additive constant. Very good. So if we act with the Wilson line of magnetic charge m, or Qm, right, then this will create a string of the corresponding tension. And now I'm going to get my area, because now I have a factor of t here for the time length, and here I have a factor of r. So this is going to be e to the minus sigma times the area of this loop. So this is the famous area law. You see that it's an exponential decay. Right? The strings have finite tension, so it's like they're very massive objects. So this is like an exponential decay of a kind of gapped correlation function. And this exponential decay is definitely faster than the perimeter decay, right? So this, this potential, the static potential between Qm and its conjugate grows linearly with the length of the string. And we said before that as long as the potential grows faster than constant at infinity, then the expectation value of the loop is 0. So this goes to 0, and then there's no VEV. Right? And that's the kind of statement that the U1 magnetic is unbroken here. Now, let me make a few comments. This mechanism of having an unbroken one-form symmetry by the creation of, or the existence of stable finite tension strings is kind of, I mean, it's like the paradigmatic mechanism for having an unbroken one-form symmetry. And I'll say a few words about the role it plays in confinement in Yang-Mills theory in a second. But it's important to appreciate that this area law decay is really a reflection of the fact that we have finite tension strings. It's not necessary to have this area law in order to have an unbroken one-form symmetry. And in order to have an unbroken one-form symmetry, it's just enough that the potential rises faster than constant. If you want a small exercise to entertain yourself, you can compute the electric QQ bar potential in 2+1 dimensional Maxwell. and you'll see that it rises logarithmically. At long distances. That's because Coulomb's law in 2 + 1 dimensions has a log in it. And so even though this theory is free and there's no strings, it still has an unbroken one-form symmetry. Very good. So that's just to kind of prime you that people have a very strong urge to associate unbroken one-form symmetry with area law, but that's not all there is. All right. Now, this story was about an abelian Higgs model with an electrically charged Higgs field. And what we ended up showing is that the unbroken U1 one-form symmetry, the U1 magnetic, had to do with the existence of these finite tension magnetic strings. Why is this an interesting toy model to consider other than on its own right? This is a perfectly interesting model on its own right. It occurs in superconductors and all sorts of other places. But there's another reason to be interested in this model, which is that it sort of furnishes the paradigmatic picture that people have for confinement in ordinary Yang-Mills theory. And in order to understand why there's a relation, you should basically take this whole picture on the board and apply electric-magnetic duality to it. In ordinary Yang-Mills theory, as I'll review maybe a little bit tomorrow, there is no magnetically charged matter and there's no magnetic one-form symmetry, but there is an electric one-form symmetry. And it's roughly speaking believed, this is kind of an old idea going back to 't Hooft and Mandelstam in the 70s, with many, many kind of interpolations since then. It's more or less believed that the qualitative picture that you might hope for in order to understand confinement, electric confinement in ordinary Yang-Mills theory, is the magnetic dual of this picture. So if you just switch electric and magnetic everywhere you see it, you see that the U1 magnetic symmetry that we had up there turns into a kind of electric symmetry. And the fact that it's unbroken in the Higgs phase means that this kind of electric one-form symmetry would be unbroken. And this is a kind of, signature of confinement. It's associated with the fact that this, why is it associated with confinement? Because an unbroken one-form symmetry requires this potential to rise at infinity. And if this potential rises at infinity, it confines charges, right? Prevents them from going off to infinity. In order for charges to escape to infinity, this thing needs to go to a constant. Now, the second piece of the story, the one involving the finite tension string, I emphasized to you wasn't literally identical to having an unbroken one-form symmetry, but it's very closely related, and it's also believed to be true in confining Yang-Mills theories, that they're finite tension strings. But there, instead of being magnetic flux strings, there would be strings of electric color flux, right? But it's literally just a change of words. And even though this story is very difficult to make precise in normal Yang-Mills theory, analytically there's a lot of evidence from the lattice, for example, that these strings exist, that they do have finite tension, and that they play an important role in the story. All right, so we'll discuss non-abelian gauge theories tomorrow, but I just wanted to kind of flash this as an important touchstone. All right, are there any questions about this? Yeah.
I'm not sure why. Well, the fact that the tension is, you assume it to be positive, is it a fact of a calculation?
Well, it's like tension is like a mass. I mean,
yeah, I mean, we know, for example, in string theory for orange strings and about strings with negative tension.
These are very long strings. These are not in string theory. You're talking about short strings. All sorts of funny things can happen. These are infinitely long strings with finite positive tension. They're like very massive particles. Yeah. Other questions?
What is the phase translation between the Coulomb phase and the Higgs phase? Sorry? Is the phase translation between the two phases
Yeah, there is a phase transition between the two phases. Thanks for asking that. I should have emphasized it more. We have, in the two phases, right, different realizations of the one-form symmetry. In the Coulomb phase, U1 magnetic is broken. And in the Higgs phase, U1 magnetic is unbroken. So we have a kind of realization of the Landau idea that there's a symmetry which is broken in one phase, unbroken in the other, so there must be a phase transition in between. Now it's generalized to these one-form symmetries. That's true. Now, the order of the phase transition in general is a difficult dynamical question. In 3+1 dimensions, this model is weakly coupled. So you can analyze it. And famously, Coleman and Weinberg showed that the phase transition is actually first order. The reason is that there are important quantum effects that become important when the particles go near the phase transition, become massless. And the quantum effects turn what looks naively like a second order transition into a first order transition. But for example, in 2+1 dimensions, the analogous model has second or first order transition depending on the parameters.
But in 3+1D, can the phase transition be in principle second order?
I mean, based on just symmetry reasoning, yes. But in this model, it's actually first order. It's computably first order.
If it's second order, is there a field theory that describes the phase transition?
I mean, let me give you the analogous answer in 2+1 dimensions, where there is a. No, you don't want that? You want 3+1.
I think there is a field theory description, but through like a mean string field theory point of view, that does interpolate in the two.
No, but if the transition is second, the mean string theory. I mean,
mean string field,
yeah, you know, that's a mouthful. I don't know if anyone's done an actual calculation using that. It's more like that was cooked up in order to reproduce the answers we know to be true from other points of view. I mean.
But I don't understand the question. So, is it just a question if there is any field theory which realizes second order phase transition for U1 magnetic?
Yeah, is there any, or one
so
can
it can be
rule it
arbitrarily
out?
complicated?
No, I don't think one can rule it out. I don't think one can rule it out. Yeah, I wouldn't. I have no doubt that such a. Actually, if you just want an example, I can cook up an example. If you just add, I think, something on the order of 20 fermions to this model, maybe it's 30, I don't care, then the transition becomes second order. Because the effect of the fermions on the Coleman-Weinberg potential is to go the opposite way. So, yeah. So if you just want proof of concept in this model, it can definitely be done. Yeah. It's not very natural. I think, yeah. All right. Now, this is sort of this question about the phase transition between Higgsing and confinement. Between Higgsing and Coulomb here, in some moral sense, didn't really require you to know about the one-form symmetry. I mean, the one-form symmetry is a nice way of saying what the answer is, but clearly you have a gapped phase on one side and you have a gapless phase with a photon on the other side. So regardless of whether or not there's a symmetry, there definitely had to be a phase transition in between. Things are more interesting if you are comparing phases that are not ostensibly different. So, for example, you could take a Higgs phase, like the one that we were discussing here, which is kind of gapped. And if the charge of the Higgs field is 1, then it's gapped and boring. And you could take a confining phase of some gauge theory, which is also, in the simplest cases, gapped and boring. And since you have two gapped and boring phases, you don't really know how to distinguish them. And so this fact will be important tomorrow, and we'll discuss, to what extent you can distinguish Higgsing and confinement using symmetries, using SPTs, and things like that. But anyway, that's for tomorrow. All right. So, if there are no more questions, are there any more questions about this abelian Higgs model? Because if not, I'm going to switch gears and cover a different topic that I kind of wanted to discuss.
So
Yeah.
In IR, the Higgs phase is SPT.
it's a non-invertible TQFT, right? It's a ZQ gauge theory with vacuum degeneracy, right? Remember one of the criteria that Max had in his lecture is that there was no vacuum degeneracy on the torus. This model has vacuum degeneracy on the torus. Yeah, there was a question there.
So in the IR, you said there's surface operators. So I guess that's, if I want to think of that as a symmetry, it's emergent.
Nope, it's not. It's not emergent. It's the spontaneously broken ZQE one-form symmetry. The ZQE one-form symmetry, because it's a one-form symmetry, it has surface operators, right, that generate it. And those surface operators precisely flow to the kind of B Wilson surfaces in the IR TQFT. Because the symmetry is spontaneously broken, the charge can't flow to zero. It has to flow to a non-trivial operator. And in this case, it flows to these Wilson surfaces of the little B field. By contrast, the surface operators that represent the U1 magnetic are not there in the IR. Because that symmetry is completely unbroken. It doesn't have to act in the IR. And there's nothing in this BF theory that plays the role of the U1 magnetic surface operators.
So I guess there's line-like defect operators, right? But those, I guess those aren't a symmetry.
No, those are the IR limit of the Wilson lines. The Wilson lines are not topological in the UV, but they become approximately topological at very long distances.
So that's not a symmetry.
No. Well, if you wish, it's an emergent symmetry. It's an emergent two-form symmetry, which is generated by charge operators that live on lines in 4 dimensions.
So the symmetry doesn't show up in this BF.
No, it does. I mean, so this BF theory has 2 symmetries. It has a ZQE one-form symmetry, and it has a ZQE two-form symmetry. The ZQE two-form symmetry is emergent and is generated by the topological Wilson lines of the A gauge field here. But that's an emergent symmetry. The A gauge field is really not topological in the UV. All right. So for the last hour or so, I want to switch gears and I want to talk about a different system, a system with fermions, and a system that's going to enable us to talk about a different aspect of higher form symmetry, which we haven't seen yet. So I introduced kind of higher form symmetry, one form symmetry as a natural generalization of zero form symmetry, and we had some simple models that had the symmetry. But right as of now, we haven't really seen an interesting interplay between zero form symmetries and one form symmetries. They kind of lived in slightly different universes. And so now I want to go through an example where they really kind of are fused together in a single structure. And this is just one simple example. It's just the tip of the iceberg, really. But this example is a good way to get a gist of what's going on. So we're going to discuss QED in 4 dimensions, massless. QED in 4 dimensions. And we're going to take NF flavors. And in particular, we're going to take more than one flavor. This model can be UV completed in various ways in particle physics. Maybe you'll hear about that from Clay. I'm just going to view this as a kind of nice model in the IR. Right now, it's just a toy model to talk about some symmetries. So, maybe you should say that a good reference for what I'm going to talk about in the rest of this lecture is this paper I wrote with Clay and Ken and Trilligator called Exploring Two-Group Global Symmetry, where we analyzed a lot of models of this type and slightly more complicated ones and explained how two-group symmetry works there and how anomalies are matched. So I'm just going to give you really the simplest example of a two-group that I know of in this context. So in order to discuss the two-group, we're going to have to discuss the chiral symmetries of this multi-flavor QED. So instead of presenting the theory in the standard way as being a theory with Dirac fermions, I'm going to split my Dirac fermions into 2-component Weil fermions. So I'm going to have n flavors. I is going to be a flavor index running from 1 to NF. And then I have each flavor splits into a left-handed and a right-handed. Weyl fermion. And as you'll see, the flavor indices on the left-handed and the right-handed Weyl fermions don't talk to each other when there's no mass. So we're discussing here massless QED. By the way, and for these two-component Weyl fermions, I'm using kind of Wessenberger two-component Weyl fermions. We'll not need to get into the conventions and so forth very heavily, but just so you know where this notation is coming from. So this is the Lagrangian of QED. Then we have our Maxwell term. And then we have the left-handed fermions. All of them will have electric charge 1. So this is the sense in which it's normal QED. Right, you see in the covariant derivative, I put charge 1, and the right-handed guy will have charge -1, and this will immediately take care of gauge anomaly cancellation. I'll say something about that in a second. And here I should be careful to make sure that the chi's have tilted indices and the psi's have untilted indices, so you see these don't talk to each other. If I add a mass term, they get fused together, but here they're independent. Where's my eraser? Interesting. Eventually this will be a problem. Right now I still have some board space here. Nope, not obviously. Ah, it's here. Good. Yeah. Okay, so basically, you know, the thing I would like to do is I would like to discuss what is the symmetry of this model. Well, there are various ways of going about that, some more sophisticated, some less. So I'm going to try to be very unsophisticated and start with a kind of a naive analysis. And the naive analysis is going to be wrong. It's very important that I say that now. So I'm going to sketch something that is not going to turn out to be correct. And then we'll have to fix it in various important ways. So let's start with the naive part, right? So imagine that we don't gauge the U1 vector symmetry of QED, right? Imagine that we just start with the free fermions. We have NF left-handed guys. We have NF right-handed guys. So they have separate UNF times UNF flavor symmetries that act just on the left and on the right. So this symmetry only acts on the psi's, which are in the fundamental, and this symmetry only acts on the chi's, which are in the fundamental. Right? Very typical with vector-like gauge theories. And now we would like to figure out what happens when we actually do gauge the U1 symmetry of QED. The U1 symmetry of QED is the vector-like diagonal U1, right? That's the diagonal linear combination of U1 left and U1 right. So we're now going to gauge U1 vector. Now, of course, the first thing that will happen when you gauge U1 vector is that U1 vector is no longer a global symmetry. So you should delete U1 vector from this picture. And you sort of formally divide by it. And then we have to figure out what to do with the rest. Notice, first of all, that we do not get any electric one-form symmetry in this model. These fermions have electric charge 1, right? So just like in the example with the Higgs field, if you include the fundamental minimal unit of charge, there's no electric one-form symmetry. But just like in that case, there is a U1 magnetic one-form symmetry, because we're dealing with a standard kind of gauge theory with only fundamental electric charges, no magnetic charges. Very good. Yeah.
So in this case, the electric symmetry is never restored at any scale, but you still have two polarizations. So how is that compatible with the statement from before that the two polarizations come from U1 electric and U1 magnetic?
Well, it's actually a subtle question whether you have two polarizations. Well, you know, if you add a mass to this model, right, so that you were talking about ordinary QED, then you can talk about physics below the scale of the electron mass, and we get back to a standard Maxwell theory with two-photon polarization. But if you're exactly in massless QED, then the photon actually, there is no single photon sort of particle in this theory. One way of phrasing that, which is kind of standard, is to say that this theory has very bad infrared divergences. But you can also argue that the photon two-point function cannot have a single particle pole, right? So there's a cut that kind of goes all the way into the pole. You can argue that using the RG. If you look at the FF two-point function in position space, it kind of looks like x to the 4th, and there's a log x. And this means that there is no real sense in which there's ever a photon, single photon state in this theory. And that's actually important for various kind of consistency arguments about RG flows. Because, well, I don't know if I'll get back to this later, so maybe I'll say it now. It will turn out that the correct point of view on the U1 magnetic in this problem is actually that the U1 magnetic is unbroken for the exactly massless theory. Because, again, if it were broken, then Goldstone's theorem would tell you that you would have a pristine, unspoiled kind of single particle pole here, and the screening from the massless electrons ruins that. Yeah. Okay. So the naive guess for the symmetry of this theory, as I said, this is naive and incorrect. We'll soon fix it. Is that the zero form part is this, and that the one form part is this, and they don't talk to each other. Okay. So this is incorrect, and it turns out to be incorrect for at least two reasons. One is very old, and one is a little less old. So the very old but ever new reason has to do with the U1 axial. So basically, the overall slogan of why this answer is wrong is because of triangle anomalies. And it turns out that triangle anomalies will do two things in this model. First of all, the U1 axial has an ABJ anomaly, an Adler-Bell-Jaquiev anomaly. Meaning an anomaly of the type that they wrote about in the 60s, 1,000 years ago. And this model has it, and we'll have to discuss a little bit what it does. You'll probably hear more about it from Shu Heng next week, maybe also from Clay. And the second thing, which is not directly tied to the U1 axial symmetry, is that it turns out that triangle anomalies also deform the direct product of G0 and G1 into a 2 group. As I'll say in more detail soon, a 2 group is a situation where the 1-form symmetry and the 0-form symmetry are not a direct product. Instead, one is an extension of the other. The 0-form symmetry is extending the 1-form symmetry. All right. So I will focus mostly on this second thing, but I'll say also a few words about the first one. Well, maybe I should say it now. Right. So just to get it out of the way so we can focus on the other anomalies. So we're going to be discussing triangle anomalies in this model. And so triangle anomalies come from diagrams that have a fermion loop going around the middle, and then 3 insertions at the edges, and the insertions can either be flavor currents or they can be dynamical gauge fields. In this case, they can be photons. And the original ABJ anomaly for the axial symmetry involves a diagram where you have, okay, this is the triangle diagram. You have two dynamical photons, photon, photon, and then you put an axial current here. And this diagram has the consequence that the divergence of the axial current is F wedge F. F wedge F is a non-zero operator, so this current is simply not conserved. And then there's a long and interesting story about what that means. But there's no debate that this current is not conserved. Whether or not the symmetry is actually broken depends on the context. There's some cases, there's some problems for which it is effectively unbroken, like in flat space. If you just study the S matrix in flat space, it actually has this symmetry. It's electron helicity. If you study certain problems that involve 't Hooft lines and monopoles, then it's not a symmetry. And this weird fact that it's sometimes a symmetry and sometimes not a symmetry, depending on the context, is a kind of modern reinterpretation in terms of saying that it is in fact a non-invertible symmetry. So you'll probably hear more about that. And that is all I wanted to say about the axial symmetry. So we're just going to forget about it. What I want to talk about next is point 2. Because this is not the only triangle anomaly in this model. There are other configurations of currents that you can imagine studying. The most obvious one involves putting just external photons on the triangle diagram. This is the pure gauge anomaly. But of course, if you sum the two diagrams, then this gives you 0, because this model is anomaly free. But it turns out that we haven't exhausted the set of possible configurations of photons and currents just yet, right? And so it turns out that there are two more interesting configurations that we need to talk about. So basically what I want to explain now is how we get, well, maybe I'll start over here, how we get two-group symmetry from triangle anomalies. Right, so okay, so here we had just photons. Here we had two photons on the U1 axial. Now we want to forget about the U1 axial, but we still have a lot of symmetry left. If we forget about the U1 axial, we can completely forget about the U1s in this problem. We can just replace these UNs by SUNs. Right? The U1 vector has been gauged, and the U1 axial you have dispensed with. And so we have this chiral SUNF left times SUNF right that acts on the left and right-handed electrons. And we would like to discuss anomalies involving the corresponding currents. So in principle, there are currents which I can call J left, which carry an adjoint index under SU2 left. And then there's currents called J right, which carry an adjoint index under the SU2 right. Now, luckily, I only need to study half of them. Why do I only need to study half of them? Because if you consider the diagonal vector-like SUNF symmetry, that acts on full Dirac fermions. And it's actually consistent with putting a mass here. Right? The diagonal symmetry is compatible with giving the fermions a mass. And that means that it cannot possibly be anomalous. Right? So the SUNF vector is non-anomalous. And that means that it's sufficient to study either left or right currents, because one linear combination of them is non-anomalous. So let's focus on the SUNF left currents. So remember, the SUNF left currents, I mean, these are literally, psi bar sigma mu psi with some kind of, generator of the SUN symmetry. And no chi's. All right. And these psi's form a single copy of the fundamental of SUNF. Very good. So now we can make triangle diagrams where we either insert photons or we insert J-left currents, right? And now we can try to think about what kind of configurations of triangle diagrams are allowed. I already discussed the triangle diagram with 3 photons, so that's been dealt with. Let's consider first the triangle diagram involving 3 currents. That's probably the next most familiar one. So we can have a triangle diagram, well, which essentially computes a correlation function of three of these J-left currents. Right. So this leading order corresponds to a triangle diagram where we simply insert these currents here, here, and here. So this is JA, nu, JB, nu, and JC rho. There's also, and then there's the diagram of the fermion going the other way. I'm not drawing that, just imagining it. Right. And so here is the point where I assume that you all learned something about triangle diagrams at some point, or you maybe did the exercises yesterday that the organizers put together. And then you learn that when you compute this diagram, it has it has many interesting properties, but the most kind of vanilla and elementary property is that if you take the divergence of this 3-point function with respect to any of its legs, let me take the divergence with respect to the first current here. So I take the dx derivative with respect to the mu component. This is simply non-zero. Now, how badly non-zero is it? Well, it's almost zero. It's not. It's basically a delta function C number contact term. I'm not going to write down the formula because it involves some derivatives and some epsilons, which I don't want to get into. But essentially, it involves products of delta functions that forces all of these 3 currents to be at the same point in space. So you get a derivative and delta function, derivative of a delta function, and then some epsilon symbol to get the tensor structure right. So this is a situation where we say that the currents are conserved at separated points, right? As long as the x, y, and z coordinates are not touching each other, the currents are actually conserved. So they're genuinely conserved currents. The symmetry is genuinely a symmetry. But they have this kind of fairly benign C number contact term when they come together. This is the correlation function analog of the kind of C number at 't Hooft anomaly we saw earlier in the context of the one-form symmetry. So when you couple this model to background fields, I'll write something about background fields in a second, this contact term in the correlation function will turn into a C number variation of the effective action under background gauge transformations. All right. So let's do that. Let's introduce somewhere.
So you don't need an F larger than 3 to have this anomaly?
This particular anomaly that I'm about to discuss requires NF bigger than 3. The 2 group will not require it. The 2 just requires NF bigger than 1. Yes. I mean, of course, for an F equals 2, there's a kind of like a Witten global analog of the anomaly I'm about to write, but there's no triangle anomaly. Right. So let's turn on background fields for these J-left currents. So let's add to the Lagrangian, being here a bit schematic, but let's add to the Lagrangian background fields that couple to these J-left currents. Well, they should be standard vector fields. Let me call them L. Well, it doesn't matter if I call them L. I can call them A. I don't want to be too confusing. Let's call them big A. Big A are the background vector fields that couple to the SU and F left. And then they're kind of like nonlinear Siegel type terms that you need to add to have full SUNF background gauge invariance. So in principle, if you want to do that, the way you do it properly is you in these covariant derivatives, you turn on covariant pieces of the covariant derivative that contain the SUNF left gauge field with the appropriate matrices in the fundamental representation. Okay. Now, when you study the model in the presence of these background fields, this kind of anomalous contact term in the 3-point function of current leads to something much more intuitive, right? It leads to a non-vanishing divergence for the, let me erase the ABG anomaly. It leads to a non-vanishing divergence for the SUNF left current in the presence of background fields. Right, so the anomaly implies that the derivative of the J left current, and here we can write either the covariant derivative or the ordinary derivative, because I'm going to be sloppy about higher order terms anyway. And on the right-hand side, we get an object that has 3 adjoint indices of SUNF and is totally symmetric. And then you get something that is essentially F wedge F, but not quite. Right, so here I'm basically just writing the leading order terms, then they're non-abelian completions. These are the terms that actually come from the triangle diagram. These higher order terms come from squares or pentagons. This DABC is a invariant tensor of my SUNF group, and as Son said, it's only present if we have SUNF with an F at least 3. Then this invariant exists, and you get an anomaly coefficient that sits out here. In suitable units, this anomaly coefficient is 1 because I have a single copy of the SUNF fundamental representation. All right. Now, this form of the equation clarifies a lot of properties of the anomaly. So the first important thing is that this little contact term over there has turned into something that only involves background fields on the right-hand side. Right? And by the way, this non-conservation of the current is tantamount to saying that the variation of the action under a background gauge transformation is this right-hand side. Right? Because when you do a background gauge transformation, you spit out the gauge parameter times the divergence of the current. So that's why I was saying it's similar to what we did before with a one-form symmetry. Because this right-hand side only involves background fields, it means that when you turn the background fields off, when you study the theory in flat space, the symmetry is actually conserved. The current is actually conserved, the symmetry is there. So this kind of anomaly with a C number right-hand side is called an 't Hooft anomaly. And you see, this is an example of an intrinsic 't Hooft anomaly that only depends on the group SUNF. In the Maxwell theory, we had a mixed 't Hooft anomaly involving 2 symmetries, U1 electric and U1 magnetic. Here's just SUNF. And then you can go ahead and do all the things you usually do with the 't Hooft anomalies. You can match them in various phases. And so this particular equation with this particular coefficient has to be there no matter what you do to the theory, as long as you don't break the SUNF left symmetry. So you can now go ahead and deform this theory. You can add scalars, you can add more fields, you can deform it to this phase or that phase, and then you have to match the anomaly. Okay, that's a beautiful and relatively standard story. Of course, the more famous context for chiral 't Hooft anomaly matching of this kind is in QCD, where the SUNF left and the SUNF right act on the quarks. So we're not going to discuss that. Very good. I mean, 't Hooft anomaly matching is always good and fun and interesting, but it's most useful when the theory that you're discussing is strongly coupled. This theory is a weakly coupled theory, so there's nothing interesting to match. The matching just happens because they're weakly coupled fermions around. Okay, so this was warm-up. We have now discussed, I think, the 3 triangle diagrams that are the most familiar. The pure gauge ones, which always have to vanish. In any gauge theory, the gauge anomalies have to vanish. We've discussed a little bit the ABJ anomaly, which is also much more violent in non-abelian gauge theories. And we've discussed a pure 't Hooft anomaly for just global symmetries. It turns out that there's one triangle diagram we haven't discussed yet. And this triangle diagram is very particular to QED. It doesn't exist in non-abelian gauge theories. It requires an abelian gauge group. And that's a triangle diagram involving only one photon and two currents. So that's the one that's going to lead us to the non-trivial 2 group. All right. Let me get the stick again. Let's see. All right, so here's the last triangle diagram. So this is going to be the photon, J left, or photon you can think of it as an insertion of F. 3-point function. And so this is a triangle diagram. Let's put the photon here. And then we have an insertion of J left A here and J left B here. Okay. Why is this diagram only present in abelian gauge theories? Because, well, yeah, because roughly speaking, when you actually compute the value of this diagram, you'll find that you get sort of sums of electric charges, linear sums of electric charges, because you have only one insertion of the photon, and typically, when you have a non-abelian generator, that vanishes.
For the non-special groups.
For what?
For the non-special groups.
Non-special groups.
Trace of the generator.
You mean simple? When you have a simple gauge group, a compact simple gauge group like SUN or something like that.
But what about UN?
No, UN has a U1. So that's what I mean. You need a U1. Right. Very good. Yeah. So this U1 could be the U1 central U1 inside a UN. So what I'm saying here involving this triangle diagram is not sensitive to the global issues of how this U1 is embedded in some higher group. So it doesn't matter if it's U1 or U1 modulo some quotient. In UN, the U1 is modded out by some quotient, but that won't matter here. This is a completely local discussion. Okay, very good. So what does this diagram lead to? Well, the previous diagram involving only J's, right, led to a non-conservation equation, which you can't read anymore, where on the left-hand side we have the divergence of J, and on the right-hand side we have 2 copies of the background field for J. So roughly speaking, what we're doing in this diagram is we're taking one of the J currents and replacing it by a dynamical photon. So the way that this is going to affect this non-conservation equation is that it's going to be replacing one of these non-abelian background fields on the right-hand side by a dynamical photon field. So instead of having this C number expression on the right-hand side, we'll have an expression of the following type. We'll get the divergence of the left-handed current. That's going to be up to some 2 pi's, which are not going to be important for me, some anomaly coefficient k times the background field for the SUN F symmetry, wedge the dynamical photon field, little f. Right. And then also other terms. So, at the level of swapping out one of the J's and plugging in a photon, this is pretty intuitive. You can check that it's right. But the thing that you're left with is to understand what this equation is supposed to mean. Right? Each one of these triangles means something different. The pure gauge triangle is an inconsistency. The ABJ anomaly involves some breaking of a symmetry. The pure 't Hooft anomaly doesn't involve any breaking of a symmetry. Instead, it's just something nice that we can match. So the question is, what does this guy do? And it turns out that this equation is tantamount to saying that the one-form symmetry and the zero-form symmetry and the one-form symmetry form a two-group. All right, and so that's what I want to explain in the rest of the lecture. So I should also say that even though I've been sloppy about factors of 2 pi, if you are careful about the factors of 2 pi, this is a quantized anomaly coefficient. So you normalize it in some way that it's integer. And you compute it from this triangle diagram, right, as usual. All right. So the first thing to do is to turn off the background fields. That gives you the kind of best intuition about what the anomaly is. Right? Remember that in the ABJ case, there was a non-zero right-hand side that didn't turn off ever. In the 't Hooft case, the right-hand side was a pure C number. So in particular, it is 0 when you turn off the background fields. This thing is kind of in between. It's not a C number. This is F. This is the dynamical photon. This is an operator. This is a C number. So when you set this background field to 0, and you study the theory in flat space without backgrounds, it is true that the current, the SUNF left current, is conserved. So there is SUNF left symmetry. It's not like the ABJ anomaly where there's some discussion about is it broken, is it not broken. It's definitely not broken. So then the question is, what is this equation supposed to encode? Well, in order to understand that, let's take this anomalous conservation law, and let's do what I said before. Let's use this anomalous conservation law to determine what happens to the path integral when we do a background gauge transformation for the SUNF gauge field, this big A, right? So let's take the path integral of this theory in the presence of background fields, and let's do a gauge transformation where we shift the SUNF left background gauge field by d of some gauge parameter. And here I'm, again, only keeping track of the leading order terms, forgetting the higher order ones. So I'm imagining doing this kind of inside the path integral, right, at the level of the path integral measure. I haven't done the path integral yet. That's very important. So what happens when I do this background gauge transformation? Well, what will happen is that the fermion measure in the path integral is going to spit out something that looks like the gauge parameter times the divergence of this SUN left current, right? So the path integral measure, if you wish, the fermion measure, or the fermion determinant in the way that Max did it, shifts. Well, let me not even be fancy. Let me just call it deep psi. This is the whole fermion measure. This shifts by an exponential of the gauge parameter times I times this anomalous divergence, right? And you're going to get an integral of that. Everything is position dependent. You're going to get this anomalous divergence, and so now I can plug in. I get K, dA, wedge F. Everything is a function of x, and then it's integrated over all of space-time. So this is happening at the level of the path integral measure, and the reason I keep saying that it's happening at the level of the measure and not at the level of the partition function is that the partition function is a number. We're used to the idea that anomalies transform partition functions by phases. But partition functions are numbers, and this thing is not a number. So you can't say that the partition function transforms by this. Instead, this is happening under the functional integral. And you see that if you just look at the fermion contribution to the functional integral, the triangle anomaly spits out this anomalous phase, which is not quite a C number. So we now have a kind of problem, right? We we are trying to say that SUNF left is a symmetry, right? I was trying to argue for that by saying that this is 0 when we turn off the background fields. But when SUNF left is a symmetry, we should be able to couple it to these background fields, and we should be able to do background gauge transformations. And now we're kind of failing. And the important thing is that we're failing in a way that's worse than with usual 't Hooft anomalies. All right. So what's the way out? Well, the way out is to recognize that the operator that is causing our failure, the operator that appears on the right-hand side here and here, is not some garden variety operator. It's actually the field strength F, and in particular, it is the conserved magnetic current of the U1 magnetic symmetry of this model. All right? So we already know that that's a good symmetry of the model, and we already know that F itself also couples to a background gauge field. That's what we discussed in the Maxwell theory and in the abelian-Higgs model and so forth. Where should I write it? I'll write it here. So remember what that coupling looked like. We had a magnetic gauge field, B magnetic, which is the background gauge field for magnetic flux, and the coupling looked something like this. Just copied over from what I did in the other models. Okay? This is not a square, this is just a superscript 2. All right. So now we are sort of in good shape, because we have an anomalous variation under SUNF background gauge transformations that is causing us a problem, but the problem is linear in F. And we have a source, B, which is already there to begin with, which also couples linearly to F. So we can fix our problem by modifying the action of the SUNF gauge transformations on B. Now, previously, B was just living happily on its own, and it had its own one-form gauge symmetry transformations, right? B transformed like this by some d lambda magnetic, the one-form gauge parameter, but it absolutely had no interest in zero-form background gauge transformations. And now we see that this is forcing upon us to assign also to B a particular transformation rule under SUNF gauge transformations. And roughly speaking, it looks like that. You can put a minus sign just to emphasize that it's supposed to cancel this with a coefficient k, and then you put the gauge parameter, and then you put dA. So let's just see that a few elementary things work out. B is a 2-form, this is a scalar, and this is a 2-form. So I'm shifting a 2-form by a 2-form, so at least that's OK. And this shift of B depends completely explicitly on the SUNF background fields and also on the gauge parameter. Now, if you are a string theorist, even distantly related to being a string theorist, then you recognize this as a version of the Green-Schwarz mechanism in string theory. This is a version. This formula is literally the Green-Schwarz anomaly cancellation formula. The main difference is that in the context of the Green-Schwarz mechanism, all the fields are dynamic, or you're trying to cancel a gauge anomaly, right? And they cancel the gauge anomaly by assigning these anomalous transformation rules to the B fields. And here we're doing essentially the same thing, but everything is a background field. Okay? So the formula is the same, and the words that you say about what it means are slightly different. And in fact, I mean, once you arrive at this, the puzzle about the non-invariance of the path integral measure has been solved. Now, everything that depends on operators like F is invariant, and depending on whether there are 't Hooft anomalies, there may or may not be C number phases, but this problem has gone away. And this particular transformation rule of the B field is one of the many equivalent ways in which you can characterize a two-group symmetry. So this is one definition, if you wish, of two-group global symmetry, the U1 magnetic is, well, is extended by the SUNF. And the way you can see that the U1 magnetic is the normal subgroup and the SUNF is the one that's extending it is by the fact that this formula is asymmetric, right? So B transforms under lambda, but A, the SUNF background field, does not transform under these big lambda transformations. So if you only do U1 magnetic background gauge transformations, that's a completely closed subgroup. But the moment you do SUNF background gauge transformations, you of course shift big A, but now you also shift B. So the SUNF background gauge transformations always touch both. And if you know something about extensions, you know that they're characterized by some kind of group cohomology classes. And this integer k, this anomaly coefficient k that came from our triangle diagram, is the thing that dictates the non-trivial extension class. Some kind of H3 class, kind of Postnikov class, that characterizes the two-group extension.
So,
yeah.
Is there an analog of an obstruction to have extension like this? Like in finite groups, there is like a H3 class that signals that there cannot be an extension of one group by another. Mm-hmm. Is there something analogous here?
There might be, in the sense that I certainly know examples where, in order to solve this problem, you can't just stop at one-form symmetries, right? Sometimes you have to actually. Sometimes you are in a situation like that, then you do this, and you kind of solve the problem at leading order, and then it turns out that there is still an operator-valued contribution in the path integral, and then it turns out that there's an even higher group symmetry that you need to involve in the game. So sometimes it's not enough to just stop at a two-group. You need to go to a three-group or whatever. I mean, in any dimension, there's a kind of highest dimension that is allowed for an n group. But yeah, I think such situations definitely exist. We might even have some examples in the paper if I remember correctly. Yeah, so you basically need to keep going until all these kind of operator contributions are canceled, and you're left with a pure C number. Yeah, and that dictates the full extension. And of course, you better hope that you always have enough higher symmetries around to play this game, but it turns out you always do. Right. Now, so we're sort of coming up on the end. I want to leave time for questions, but I want to say one or two more things about the fact that this symmetry is a non-trivial group extension, which is that. So when you are in a situation like that, there's a kind of asymmetry between the two players, right? Between the zero form and the one form symmetry. And that's interesting enough if you just have the whole symmetry. If you have the whole symmetry, you can try to exploit this structure. You can try to look at its word identities and its consequences and so forth. But it turns out that most interesting examples of two groups that occur in kind of physically relevant or semi-physically relevant models are not ones that have exact two-group symmetry. The most interesting examples have emergent two-group symmetry. The reason is that essentially, from the get-go, if you want to consider a continuous two-group like the one I'm discussing here, you need a U1 gauge field. And a U1 gauge field, I mean, depending on your worldview, is not something particularly nice to have at short distances, but it's definitely nice to have at long distances. And even if you have a U1 gauge field, you might be in a situation where you have dynamical magnetic monopole, so maybe this one-form symmetry is broken at short distances. In any case, the situation when you have a two-group that isn't exact but emerges it turns out to be constrained by this extension structure. The fact that U1 magnetic is a subgroup, but SUNF left is not a subgroup. And this fact, I think, will be used in Clay's lectures when he discusses, particle physics models. So I just wanted to kind of preview this fact. Very good. Okay, so I think that's all I wanted to say about two groups. I'm happy to take more questions. Yeah.
Will you say something about the consequences of this two group? Like what are the signatures?
Well, if I had more time, I would have said more about the consequences. But you know, once you understand that you have this structure, you know, you can play essentially any game that you play with any other symmetry. You can, for example, ask in a given phase, is the group the symmetry broken or is it unbroken? And maybe this gives a toy example of what I was just sketching, even in this QED theory. So let me say it. So before we get to anything sophisticated like anomalies or anomaly matching, let's just discuss the spontaneous breaking, right? So here we have a model in which we have fermions, no Goldstone bosons for the zero form symmetry. So the SUNF symmetry is unbroken, right? But based on what I just said, that immediately implies that the U1 magnetic must also be unbroken, right? Because if the U1 magnetic were broken, then you would have a breaking pattern from the whole two group, U1 magnetic extended by SUNF, down to SUNF. But SUNF is not a subgroup of the two group. U1 magnetic is, but SUNF is not. So it turns out that in this model, the moment you know that SUNF is unbroken, you also know that U1 magnetic is unbroken. And that's something that's slightly non-trivial. It relates to the question that Diego asked before. And it turns out to be true in this model that U1 magnetic is unbroken, precisely because the massless fermions screen the Goldstone pole of the photon and make it so that there's no single photon state in the spectrum. So this is not completely obvious. You know, the two group involves a chiral SUNF symmetry, so it's very crucial that the mass is zero. At the moment you add an electron mass, this chiral SUNF disappears, and the two group also disappears. And so the fact that the electron is massless is precisely the thing that screens the photon away and gives you a consistent breaking pattern from the whole two group being unbroken. If you ever encounter a situation where you think that this is unbroken, but this is broken, that's inconsistent with the two group. So this is already a simple illustration of this of the use of this extension.
What happened to the top line?
The Tuft line, well, it decouples from the low energy theory, though precisely the rate at which it's decoupling, I don't know if it's been actually calculated. It's very similar, it's very similar to the way that monopole operators decouple in 2+1 dimensions if you go into the UV. Right? Roughly speaking, in 2+1 dimensions, you know that if you go to very short distances where the gauge coupling goes to 0, then monopole operators exponentially decouple. And here it's similar, except it's less radical. The gauge coupling is also flowing to 0, it's just flowing logarithmically. But that's enough to make the monopole operators decouple in the IR.
You don't have to worry about some zero modes on the monopole or some scattering.
I mean, yeah, you might worry about it. As I said, I don't think anyone's tried to calculate the monopole correlation function in this model. As far as I know, there are not very explicit results.
Yeah, this paper has
it's related to this. The dot loop is it even well defined to ask if it's like area law or perimeter, because sort of naively by S duality it's sort of like Coulomb 1/alpha instead of alpha.
But the S duality argument is correct in free Maxwell theory, but it's very much not correct in this theory. So here the running, here we have the electrons, right, and they break S duality. So the running of the gauge coupling, no, it gets log corrections.
It's lower than linear.
Well, so this is what I mean. So to my knowledge, maybe you probably know this literature better than I do, but to my knowledge, nobody has tried to compute the actual monopole, or monopole, anti-monopole 2-point function in this model, like the correlator of the Tuft loop. The photon-photon two-point function is easy to compute. And it's easy to convince yourself that there's no Goldstone pole, because that's essentially a one-loop kind of RG type argument. But so that tells you that the symmetry is unbroken. But it would be more satisfying to have an understanding of exactly how rapidly the 't Hooft loop decouples. If you think that it's just Coulombic plus log corrections, then indeed it's hard to understand how it could.
It seems to be ambiguous because of the Landau pole. I don't know if it's well defined at all.
That's a logical possibility, but it would be an unsatisfying one. This is an infrared phenomenon, so. Yeah, you know, this is not about how you define the monopole at short distances. This is really about the long distance behavior of its two-point function.
Yeah, to define the dot line, you need boundary condition for the Fermi, which is sort of like UV data, right? Because it's like you're defining the behavior.
No, it's much more dramatic than that. Any line that is charged under the one-form symmetry has to decouple in the infrared. So as long as it's charged in the one-form symmetry, right, and if it deserves to be called an 't Hooft line, it should be, then it should decouple in the infrared. So there might be many, so I understand what you're saying. You're saying there might be many microscopic definitions of the 't Hooft line that all differ in what you do with the fermions and the boundary conditions, and maybe they represent different microscopic monopoles, but all of them should decouple in the infrared. So it smells like there should be some kind of universal infrared computation that one can try to do to show this, but at least to my knowledge, this hasn't been done.
Define, please, what do you mean by offline decoupling in the infrared?
I mean that it's not an operator that you should think of as being present in the very long distance effective theory.
This certainly should have some more down-to-earth formulation in terms of correlation functions of the theory.
Absolutely. So remember that the thing that what we're really literally discussing now is again the static potential between the 't Hooft lines, but now we're not in the Higgs phase. So in the Higgs phase, right, so we're discussing the loop of the 't Hooft lines. Oh. This is let's take the fundamental 't Hooft loop, right, and this thing is e to the minus v monopole anti-monopole. And we're discussing the property of this monopole anti-monopole potential. Remember that in the Higgs phase it was linearly confining. What I'm saying now is that in this massless QED phase, from various points of view, you can argue that this thing has to grow faster than perimeter in order to make sure that the 't Hooft loops don't have a VEV. But the question is, how fast is it growing? And in order to do that, you have to do a kind of direct calculation of this quantity or of this quantity. And you can't use any easy tricks to do it, like in the free Maxwell theory, because you don't have S-duality anymore and so forth. Yeah. And the theory is also no longer conformal. In a conformal theory, you could map this to something else, maybe a circular loop or something. But the running of the gauge coupling is crucial here in order to get this effect, so you can't ignore it. Yeah, so it's like an ultra long distance effect. You know, like this is already a massless theory. But yeah.
You can just start with the, with the naive answer and RG improve.
That's what I did for the photon two-point function. If you do this for the 't Hooft loop, then I think that's what Diego was suggesting before. So if you just take the Maxwell answer, it has a 1 over e squared in the denominator, and then a Coulombic behavior, and then you can try to RG improve this. But that will at most modify this by some log. And the log is never going to beat the 1 over r. So that would mean that this actually goes to 0. But that's inconsistent with the loop having 0 expectation value. I think it's actually an interesting open puzzle. Well, maybe it's not open. Maybe somebody knows the answer, but it's open to me. I'm waiting for somebody to show the answer.
Maybe a stupid question. So is there any similar thing in the 2+1D?
Similar to which of these things?
Yes. Just like you gauge you want zero form symmetry in 2+1D, you will obtain another you want zero form symmetry.
Yeah, but in that case, there's something similar, but in that case, you extend a zero form symmetry by another zero form symmetry. So that's not a two group. That just tells you that the zero form symmetry is not what you thought it is.
Yes, but if we replace the U1 symmetry by the discrete symmetry.
Yeah, then you can get two groups, and there are lots of examples of discrete two groups in 2+1 dimensions. Yeah. tons and tons. And 99% are constructed from the same mechanism. You start with a model that has a kind of mixed 't Hooft anomaly, like the mixed triangle anomaly that I had, and then you gauge one of the fields.
Does the two-group structure modify the fusion rules of the generators? Each of these zero form and one form symmetries? Like roughly how? Like.
Well, I mean, there's some kind of associator which involves like a group, a move of 5 of the zero form symmetries, and that associator spits out a one form symmetry generator. Yeah. So there's a very definite kind of move that you can do that is sensitive to this K. Yeah.
Does the Bosnikov class affect the kinematics of the symmetry charges in any similar way?
No, the integrated symmetry charges, the fully integrated symmetry charges are not affected by this. So you need to either consider like higher kind of fusion moves or defect moves of the generators, or in the system that I had here with currents, you can simply forget about the charge operators and you can work directly with the currents. Remember I said in the very first lecture that the symmetry structure is encoded in the OPE of the currents and in the OPE of the currents with other operators, so you can do the same thing here.
By charges I meant the charged operators. So there's a local operator for the zero form and some loop for the one form. Do those have any kinematic interplay?
Yes, the answer is yes, but interestingly, this hasn't been like, there's been like recent work on this. There's like kind of answers in the math literature that are supposed to be the answer to this question, as you might imagine. But it hasn't like, I don't think it has been given a sort of super straightforward physics interpretation and kind of, so that's still, I think, interesting. Okay. I'll stop here. Thanks.